This is Professor Jared Rathel, and I welcome you to the first lecture of our first unit entitled The Nature of Science. So, for the next few minutes, we're going to be thinking about the defining qualities that distinguish the process of science from other pathways to knowledge. So I like to start my Biology 182 course by talking about my scientific hero, Dr. Jane Goodall. So Dr. Goodall is in her 80s now, but I vividly remember reading about her adventures in far off places in the wilds of Africa in the pages of National Geographic when I was just a boy. So to me, Jane Goodall embodies what it means to be a good scientist. So, with little more than a pair of binoculars and her trusted field notebook, at the tender age of 26 years old, Jane left England for Africa. There, she was able to habituate herself to wild chimpanzees in the forests of Gombe, and she was able to get close enough to observe compassionate behaviors in these chimps. Behaviors like hugging and kissing, tickling, food sharing, even adoption. She was also able to observe malevolent behaviors, things like aggression, warfare between the young males and the different troops, things like infanticide. Jane Goodall showed us in her own words, it isn't only human beings that have personality, who are capable of rational thought and emotions like joy and sorrow. In 1960, Dr. Jane Goodall was the first scientist to document an animal constructing and using tools. So chimpanzees will carefully select the right sticks. They'll fashion these sticks so that they can fish for termites in termite mounds. So as humans, we like to think of ourselves as apart from the animal kingdom. We like to put ourselves up on a pedestal. Before Jane, we thought we were the only ones capable of using tools. So this is what I mean by good science. So ultimately, by observing nature as an objective scientist, we learn about ourselves. So I'm showing you a quick screenshot of my guided notes. In my face-to-face classes in Bio 182, I always print these guided notes for my students. That way they can really tune in to the lectures and they don't have to worry about scrawling down every tangent that I go on. So I've also provided you with Word docs of these guided notes. You can see this is lecture 1-1, The Nature of Science, so the title is paired up with the lecture. And a couple of different ways you can do it. You can print hard copy and then fill in the notes. You can have an electronic copy up and type in the notes. But I think it would be a good idea, or you can just take notes in your notebook, freehand if you prefer. But however you choose to do it, I think it's a good idea to scrawl out some of the main ideas. And the guided notes are going to tell you what I identify as the most important concepts in the lecture, and then you can use those guided notes on your exams. So they'll be quite helpful for your weekly assessments. So my biggest hope for you in taking this class is that you recognize that science, as the famous astronomer Carl Sagan so eloquently states, is more than just a body of knowledge. It's more than just an ever increasing collection of facts. Science is a way of thinking, and I love this part. Science is a way of skeptically interrogating the universe. So let me tell you, skepticism, being skeptical, is hard. Skepticism is not the default setting for our brains. Our brains are hardwired for belief. We see circus animals in the clouds on a summer day. We see faces in the meaningless blotches of ink. We're gullible. We want to believe in supernatural forces, from gods to ghosts. Sagan goes on to say, if we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we are up for grabs for the next charlatan, either political or religious, who comes rambling along. So please, hear me now. Do not accept a claim as truth just because someone from a place of authority says it is so. Question what I say. Question what your parents say. Please be respectful with grandma. Question what your pastors and your priests and your rabbis and your mullahs and your gurus say. Question what those politicians say. Be skeptical. Demand evidence before accepting any claim of truth. So science is the best available tool that we have to discern the fundamental nature of reality, because nature is understandable. Nature behaves according to the fixed laws of physics and chemistry. So consider the tides, the timing of high and low tides at, say, Puerto Penasco, Rocky Point. Right? Those tides are not random, nor is it magical, governed by Poseidon, the god of the seas. The tides are a function of the position and the gravitational pull of the moon and the sun. Today, NOAA, the National Oceanic and Atmospheric Agency, can predict high and low tides anywhere in the world within an average of less than 5 inches, because the natural world is understandable. So the process of science works. So predicting the rise and fall of the tides, that's one thing. But what about complex living organisms? Are they predictable? Can we use this tool called science to better understand living organisms? Well, I'd like to introduce you to Tiktaalik. Tiktaalik was part lobe-finned fish. And the lobe-finned fish are like the coelacanth, right? And the mud skippers. They're the fish that walk along the bottom of the ocean. The mud skippers out in the dry air on the mud flaps on their fins. So Tiktaalik is part lobe-finned fish, but also part amphibian. Dr. Neil Shubin from the University of Chicago predicted he would find this fossil, the first vertebrate, the first organism with a backbone, with a vertebral column and 4 limbs, the first tetrapod, first 4-limbed vertebrate to make it to dry land in 375-million-year-old rock. Turns out it was in the Canadian Arctic. Dr. Shubin predicted that this transitionary fossil, part fish and part amphibian, would exist. But let him tell you the story.
My name's Neil Shubin. I'm from the University of Chicago, where I'm a professor in the faculty of the anatomy department there. I also hold an appointment at the Field Museum of Natural History, also in Chicago. So you have to understand the setting. The setting of the day we found it was, this was our last expedition to the Canadian Arctic. We were running out of money, and I'm not saying this for drama. It's really expensive to work there. We'd worked there for a number of years already with very little success. We had not much to show for ourselves. We decided to sort of spend the lot and have one last season working at that layer. So Steve's cracking rocks, and Steve is up, about 7 feet from me. He says, "Hey Neil, what's this?" And I remember looking at the thing and saying, "Okay, we have a flat-headed fish." I looked at Ted and Farish, who were the co-leaders of the expedition. We were like, "Oh my God!" I mean, it was there was two feelings. One was just incredible joy, but the other was incredible relief, which is really this is our last chance at this. And as soon as I saw what this object was, I knew we had found what we had spent 6 years, and I had spent about 20 years before looking for it. Since I was a graduate student, I was interested in one of the great evolutionary events in Earth history, which is the transition from life in water to life on land. And you think about that, it's a remarkable transition because so much in the animals have to change. So I got interested early on in this transition, and my goal was to find new evidence that tells us about how it happened. So what I did, starting in the early 90s, was to try to find rocks in the world that had the right properties to hold the fossils that would tell us about this transition. From a fish that has like a conical head and fins, to a land-living animal of the time, in the Devonian, which has a flat head with limbs. So we looked around the world, and it eventually became clear through a moment of serendipity that one of the best places and most unexplored places to look for such a fossil was in the Canadian Arctic. We discovered it from a geological textbook, not the scientific literature. It was completely accidental. But it turns out these were the perfect rocks of the right age and exposed at the surface to produce such an intermediate. And what it looks like is you have a flat head with eyes on top, and then you essentially have the body of what looks like a fish, a stubby fish, because it has scales and these stubby fins. Now what's great about Tiktaalik, it's a real melange of characteristics of fish and land-living creature. And the shape of the head, the proportions of the head, and the bones and so forth are very much like a land-living animal. And then other parts are fish-like. What's remarkable about the fin is when you take out the fin webbing, it has bones that correspond to upper arm, i.e. humerus, forearm, i.e. radius and ulna, and even portions of the wrist, the so-called proximal carpal. So a real remarkable transitional creature. It had both lungs and gills. And what's exceptional about this is just how ordinary it is, in the sense that it's exactly the intermediate that you would likely predict. So what this does is it tells us a lot about the shift from water to land, along with the other creatures. And so there are hundreds of other fossils that colleagues around the world have found. It tells us a lot about how this great transition happened. When Tiktaalik was announced in the pages of Nature, we had 2 articles, which was nice because it gave us a chance to do a lot of description, basic description of the creature. Well, it hit a lot of news headlines in April of 2006 when it came out. So much so, I was dropping my son off at school the day it was announced, and his teacher said, "Hey, bring in the fish." So I brought the cast of the fossil, which we had made at that point. I remember showing it to the kids, and I said, "Hey guys, what do you think it is?" One kid said, "Oh, it looks like a crocodile." And you could see why he said it's like a crocodile, because it has flathead eyes on top, and you can even see teeth on the side. Another kid corrected him and said, "No, it's a fish. It's got scales, and it has fins." And I said, "Hey, you're both right," because they got the concept right immediately, And so, if only adults in Louisiana would get what kids got really quickly in a preschool. What inspires me is this transition from life in water to life on land is not just some esoteric twig on the evolutionary tree. It's very important for us. It's very important because this event is part of our own evolutionary history when our common ancestor was a fish. So that this proto-wrist we see for the first time in Tiktaalik and its evolutionary cousins, something that became our own wrist. This neck that we see for the first time in Tiktaalik and its evolutionary cousins is something that was to become our own necks. Inside our organs, inside our genes, inside our cells, carry artifacts of the history of life, carry events like this, of which this is just one of countless events in the last 3 billion years.
There are different pathways to knowledge. There's science, religion, philosophy. My job as your instructor is not to try and persuade you that one pathway is inherently better than the other. My job is to demonstrate to you that these pathways are radically, fundamentally different. So, religion asks you to have faith, to believe in things that you can't see, that you can't observe, to believe in things that exist beyond nature. Science is fundamentally different. Science demands evidence. It requires us to be skeptical about truth claims unless those claims are supported by empirically derived evidence. Anybody know what this is? Don't worry about it. You don't have to worry about contracting it anymore. So this is the last known natural case reported in Somalia in 1977 of smallpox. Smallpox was completely eradicated in humans in 1980 following a global immunization campaign led by the World Health Organization, the WHO. It's evidence that vaccines work. The anti-vaxxers, they can make all the claims in the world, but there is not a shred of statistical evidence linking vaccines to an increased probability of autism, regardless of what MTV personalities would have you believe. So there's claims and opinions out there, lots of them, but science demands evidence. Good science requires a blend of both logic and imagination. As an example, consider Albert Einstein, arguably the greatest mind of the 20th century. A lot of people don't know about him. I would encourage you to read his collection of essays known as The World as I See It. But most people don't know he was a pacifist. He exchanged letters with Mahatma Gandhi. Most people don't know that Albert Einstein was a secular humanist. He was opposed to racism, right, in the early 1900s. Einstein was an ardent supporter of socialism. But the guy dabbled a little bit in science too. So let me explain. Einstein, to teach his special theory of relativity, which is really a non-intuitive concept to be sure, he imaginatively used what he called a thought experiment. So imagine a pair of twins born at the same time on planet Earth. One twin remains here, and the second boards a rocket ship that blasts off into outer space. It's a futuristic ship with an unlimited supply of fuel that allows that ship to continuously accelerate. That ship goes faster and faster and faster, and that matter, that ship and the people aboard, that matter, it approaches the speed of light, the cosmic speed limit, the fastest thing that anything can go in our universe, the speed of light. The ship takes a big looping tour around a region of our Milky Way, and then it returns to planet Earth. 90 years have passed. The twin left on Earth is old, 90 years old, and gets around using a walker. The shuttle door opens on the spaceship, and out bounds the second twin, a toddler. What? So the special theory of relativity teaches us that as matter approaches the speed of light, time slows down. The rate at which time proceeds is not fixed. It feels like it, surely feels like it from our perspective because we're trapped in this matter, in these human bodies. But time is actually variable depending upon your speed. And there have been real experiments using quantum clocks that can measure millionths of seconds and jet planes that have verified Einstein's theory of relativity. These quantum clocks actually slow down when they're on jet planes. So, difficult concept to teach. Einstein uses his imagination to teach non-intuitive concepts. The next defining characteristic of science, it's durable. So Sir Isaac Newton published his 3 laws of motion. The law of inertia, the law that force equals mass times acceleration, that for every action there is an equal but opposite reaction. He published his 3 laws of motion in the Mathematical Principles of Natural Philosophy in, get this, 1687. From launching satellites today to safety testing automobiles, our technological world is built on these ideas. So good predictive science like Newton's laws of motion are durable. They stand the test of time. That said, as our technology improves, so does our ability to observe and measure the cosmos. Hence, our scientific knowledge is subject to change. Consider that once bedrock idea of a universe. Notice the air quotes around uni. Uni means one, a singular verse, a single universe created by our Big Bang with our 26 what are known as the fundamental constants, like the universal gravitational force and the mass of an electron. These 26 fundamental constants, they determine the nature of our universe. But you can tweak these constants any number of different ways, and you can get an infinite number of iterations, an infinite number of universes. So many prominent scientists, from Stephen Hawking to Neil deGrasse Tyson and Sean Carroll, they argue that the universe, this idea of a single universe, should be discarded in favor of a multiverse, where there is this froth of universes like bubbles in my kid's bathtub. So recognize that while good science is durable, as we learn more, we refine our ideas, and science is subject to change. One of the defining qualities of the scientific process is our commitment to objectivity. What that means is that when a scientist designs an experiment to test a suite of hypotheses, good scientists, objective scientists, they don't have preferred outcomes. They don't have pet hypotheses that they hope are going to win. So I recognize it can be tricky to discern what is actual science, because oftentimes industries will invest heavily in creating pseudoscience, false science, materials that appear scientific on their surface but are inherently biased, because the industries that are paying the scientists, more air quotes, they're corrupted by the almighty dollar. So the classic example is the tobacco industry. The tobacco industry, Philip Morris, they knew for decades that their product, that cigarettes, caused lung cancer. Yet they purposefully created doubt about the growing body of scientific evidence linking smoking to cancer rates. They were biased. So this same trick was pulled by a conservative think tank called the Heritage Foundation in the early 2000s. The Heritage Foundation received millions of dollars from ExxonMobil, right, the big oil and gas producer, to purposefully create biased pseudoscience and cast doubt on the incredible and growing body of evidence linking human-generated greenhouse gases to climate change. Let me tell you, the evidence is overwhelming. The climate is rapidly changing because of human activities. Anyone who tells you otherwise, they've likely been influenced by biased propaganda, likely created by the Heritage Foundations and its scientists. But if you look to the source of the claims, they're not found in peer-reviewed scientific journals, in the peer-reviewed scientific literature. Okay, the last quality about science that I want to think about is that science is a complex social activity. Scientists that see farther, as Isaac Newton said, stand on the shoulders of giants. What did he mean by that? Science builds upon itself. So consider the first electronic digital programmable computer. It was built in 1943. They called it Colossus. This first computer weighed 30 tons, right? That's like 60,000 pounds. And it was constructed of over 18,000 vacuum tubes. So from this 60,000 pound computer made up of vacuum tubes to today, right, with our Apple iPhones, the image that you see before you, this is Deep Dream. It's a computer vision program created by Google, which uses a convolutional neural network that, once trained, creates dreamlike hallucinogenic images, like you see here with the Chihuahua, the armadillo, and the Eiffel Tower, right? So what happens when you train these computers is that they're prone to a very real phenomenon that the human brain is also prone to, called pareidolia. Pareidolia is when patterns are created from random noise. So like our human brain seeing, images in the clouds, an elephant in the summer clouds. So my point is science is building upon itself. And so you take a moment and you imagine where this wearable tech is going. So the futurists, they talk about the singularity, right? Processors becoming so small that they can actually be directly injected into our vascular system, into our bloodstream. And then these little microscopic processors will seek out and deliver medication to individual cells that are sick. This is the great singularity. Supposedly, they predict it occurs in the, I think, late 2040s, where our wearable tech merges with our biology. So don't lose yourself in the weeds here. My point is that science is a complex social activity that builds upon itself. And with that, I present to you some of the defining qualities of the scientific process. I hope you enjoyed the presentation, and I thank you for your time.